This related rate problem is a very typical, it's a kind of a standard calculus question where you have this shadow. It's cast onto the ground by that 5-foot tall person. Okay, so this is 5 and 20. And we need to relate, you're told that a person is walking away, so we'll call that length x, and we'll say that dx by dt is equal to 6 feet per second. And you're being asked, how is the length of the shadow changing? Okay, so we need to relate this x to this shadow length here. So to do that, we need to recognize that, oh, we're dealing with similar triangles here. So this big triangle compared to a small triangle, I'm going to make that ratio. 20 to 5 is big triangle to small triangle. The length x plus s is a big triangle side compared to s, which is a small triangle side. So it looks like this. The ratio is 20 to 5, big to small, big triangle side to small triangle side. There's a relationship. Once I connect s to x, then we can differentiate this implicitly with respect to time. So I could use quotient rule here, but it's way easier just to simplify this equation. 20 divided by 5 is 4. Cross multiply the s over to on that side, and we might as well group our s's together. And this ends up being just a proportion, really, because we know that this similar triangle relationship, this length changes in proportion to this length in the triangle. So if I differentiate this, I get 3 ds over dt is equal to dx over dt. I know dx over dt. I was told at the beginning it's 6 feet per second. 6 feet per second divided by 3. Okay, I end up with the change in the shadow length is going to be 2 feet per second. Okay, so this is in a ratio of 3 to 1. So if this is 6, this is going to be 2. Okay, so there it is. There's a related rate problem. This is a fairly standard one. The idea is you have to connect the variables together in a relationship and then differentiate implicitly.